For thousands of years, a wagon without a horse was simply 2 tons of dead weight. Moving across land required muscle. The theoretical challenge of removing the animal from the equation attracted some of history's sharpest minds. During the Renaissance, Leonardo da Vinci drafted plans for what we would now recognize as a self-propelled cart. Da Vinci's animated design shows incredible foresight. It features a pre-programmed steering path and a differential gear system so wheels spin at different speeds to turn corners. To keep motion smooth, a clock-like balance wheel ensures the cart rolls steadily, rather than violently lurching forward. The physics of the power source, however, doomed the project. Da Vinci relied on 2 symmetric wound springs. As those springs unwound, their kinetic force dropped rapidly. A cart built this way would travel a few meters, slow down, and stop entirely. Da Vinci successfully drafted the mechanics of steering and control, but he lacked a method for generating sustained power. Solving that specific problem would consume engineers around the world for the next 4 centuries. By the 18th century, inventors entered an era of experimentation. The goal was an artificial force capable of pulling heavy loads over long distances without exhaustion. In 1769, a French inventor named Nicolas Joseph Cugnot achieved a breakthrough, using steam. He built a wooden dray for hauling artillery. As we can see, it required a massive copper boiler hung over the front wheel to generate enough pressure to move at just 2 miles per hour. Yet it proved that machine-driven motion was physically possible. Steam posed severe physical limitations for personal transport. A boiler requires immense amounts of water and heavy fuel like coal. Shrinking it down resulted in cramped, dangerous layouts, with operators sitting inches away from scalding pressurized tanks and open flames. Looking for a cleaner, lighter solution, Scottish inventor Robert Anderson took a radically different approach. In the 1830s, he built a crude carriage powered entirely by electricity. It moved quietly and lacked the bulky weight of a steam boiler. But Anderson's carriage relied on primary power cells. They were non-rechargeable. Once the chemicals inside depleted, the battery was dead, and the vehicle became a heavy piece of yard art. A clear pattern emerged. Generating motion was not the issue. For a vehicle to be practical, its power source must be compact, capable of running continuously, and easily refueled on the go. A major theoretical leap arrived in 1807 through a Swiss inventor named François-Isaac Derivaze. He mixed hydrogen and oxygen inside a cylinder and ignited it manually with an electric spark, creating one of the earliest internal combustion engines. This diagram shows why Derivaze's engines stalled. On the left, a spark causes an isolated explosion without in-cylinder compression. On the right, we add the missing connecting rod and mechanical crank. Without these, the energy simply dissipates instead of becoming rotational force. It took another 78 years for an engineer to finally connect the pieces. In the 1880s, Karl Benz took the raw explosive power of internal combustion and successfully translated it into forward drive. Benz engineered the 1886 Patent-Motorwagen from the ground up, integrating the gasoline engine into a custom-built tubular steel chassis.
This schematic shows how the engine block became a structural part of the vehicle rather than an add-on. This design bridged the gap between the engine and the wheels through a system of drive belts and pulleys. The engine rotated a horizontal flywheel, and these belts carried that rotational energy directly to the rear axle. This completed 3-wheeled machine, the Patent-Motorwagen, successfully synthesized steering, a replenishable liquid fuel source, and continuous power transfer. It became the world's first true automobile. Benz quickly patented his design, yet a brilliant machine sitting stationary in a workshop is useless until it proves it can survive the unpredictable conditions, the steep grades, and the mechanical stress of the real world. Karl Benz was a gifted engineer, but a notoriously poor marketer. Frustrated by his reluctance to publicly demonstrate the car, his wife and business partner, Bertha Benz, took matters into her own hands. In August 1888, without telling her husband or the local authorities, she loaded her 2 teenage sons onto the motor wagon and set off on an unauthorized 106-kilometer journey to Pforzheim. Moving the car from the flat workshop floor to wagon trails quickly exposed its physical limits. The first crisis arrived at the bottom of a hill.
The vehicle was equipped with only 2 gears, and neither provided enough torque to climb steep inclines. Bertha's sons, Eugene and Richard, had to climb out and physically push the heavy machine up the hills. This exhausting failure proved an absolute necessity for all future vehicles. They required a dedicated lower climbing gear to handle changes in elevation. The next crisis involved the fuel. The motor wagon didn't have a dedicated fuel tank. It relied on a meager 4.5-liter supply of petroleum solvent sitting directly in the carburetor, which rapidly ran dry on the open road. Bertha had to improvise. She stopped at an apothecary in Wiesloch to purchase ligroin, a solvent normally used for cleaning, making the local pharmacy the world's first gas station. When the fuel line became clogged with debris, she pulled out her hat pin to clear the blockage and insulated the line with her garter. But the most dangerous moment occurred on the downhill descents. The original brakes were made entirely of wood. The intense friction from stopping the heavy cart on steep slopes began wearing the wooden blocks down to nothing. Facing total brake failure, Bertha stopped at a local cobbler. As this animated diagram illustrates, wood-on-wood contact rapidly disintegrates under heat. She instructed the shoemaker to nail thick leather to the wooden brake blocks, instantly increasing their friction and durability. On the side of a dirt road, she had just invented the world's first brake linings. Bertha Benz reached Portsheim by dusk and sent a telegram to her husband. The trip successfully attracted the massive public attention the company desperately needed, and her detailed notes on the vehicle's failures provided the exact blueprints for the next iteration of the machine. The modern automobile did not spring perfectly formed from a single notebook or a solitary workshop. It required centuries of dead ends, theoretical leaps, and, most importantly, the brute physical friction of the real world to force an idea to meet reality.